Okay, so we have already calculated the solidification time for the sphere and the cylinder. And now for the cube, what you will consider now is the volume and area, lateral area of the cube. So of course, you know that for the cube, you have uh, 6 faces, okay? And each face area will be equal to a square. This is why in total, the lateral area for the cube will be 6 times a square, okay? Then for each side, it is 10 centimeter or 1 decimeter. So we can calculate that the total lateral area is 6 times a cube, since we have 6 faces. So we can see here this in the figure. And then for the volume is a cube. So we can calculate then V over A. V over A will be equal to L cube over 6L squared. So you will have that L square will be simplified. You will end up with L over 6. And L over 6 is here uh, 6. We will get 6 decimeter square, the area, and the volume 1 decimeter square. So when you do the ratio, it's 1 over 6. So again, we got that also for the cube of for which each side is equal to 10 centimeters, V over A is equal to V over A for the sphere and cylinder with the given specifications. So what we deduce from here is that the 3 shapes will give us the same solidification time. So when you have the same solidification time for the 3 shapes, then the criteria of selection will be different. What you use, if you want to select between these 3, what you should do is you should find the what will be the criteria here? Which one you will select if they all have same solidification time? Exactly, the one with the lowest volume in order to reduce the waste. Okay, so here what we can do if we compare the volumes, you have for the sphere it's pi over 6. Okay, for the cylinder it's pi over 4, and for the cube it's 1. So of course the smallest volume is for the sphere. Okay, so we will select here the sphere because you have the same solidification time, but you have the lowest volume for the sphere. So first choice is sphere. Between cylinder and cube, you can choose the cylinder because also it has smaller volume. Okay, now before the selection, they asked to calculate the solidification time if the mold constant is given. So they gave us a mold constant of 3.5 minutes per centimeter square, uh, which is equivalent to 350 minutes per decimeter square. So pay attention for your units. If you expressed V over A in decimeter square, then you should convert your mold constant to minute per decimeter square. If you calculated your volume V over A in centimeter square, then you can use this value. Okay? So just pay attention for units. And then you can get the solidification time for the 3 shapes equal to 9.723 minutes. Here they said first that all 3 shapes are equivalent as risers. They mean in terms of solidification time. Okay? But when you want to select according to the criteria of volume, uh, then we should select the sphere based that because in this case the waste will be minimized since we will have the lowest volume. Okay, so here they should be more clear. They should say how equivalent concerning solidification time. Okay, but of course if you want, let us replace it by all 3 shapes have same solidification time. Okay, but to select we should look at another criteria. So to select we select the smallest volume. Okay. Now, any question on this problem before moving to another one? Uh, In aluminum copper alloy, composition 92% aluminum, 8% copper, is made in a sand mold using a sand core that weighs 15 kilograms. Determines the buoyancy force in Newton tending to lift the core during pouring, knowing that the sand density is 1.6 gram per centimeter cube, and the aluminum copper density is 2.81 gram per centimeter cube. So here, always when we have the core, okay, we should pay attention for two things. So first, it should be able to sustain buoyancy forces. So it should be well placed. This is why if you have covered chapter 8 part 1, I think, okay, then you will see that we have chaplets that will be used to maintain the core in its place, because you have two criteria, and we will do this in more details after, okay, in one problem in the homework. I posted for you a homework, so please try to do it on chapter 7 and 8. So here we put chaplets to fix the core to the main mold if you want. And in this case, you might need chaplets from on the level at top and chaplets at bottom. Why? Because chaplets from top can help you to overcome the buoyancy force. Why? While before pouring, before you have your fluid filling your cavity, you have the weight of the core will tend to move it down. So you should have chaplets on the lower level to oppose weight. And after pouring, because if the buoyancy will be, the total force acting, the buoyancy will be higher than the weight, then you should have chaplets at the highest level in order to oppose buoyancy. So this is why we'll see in several cases that we put chaplets from the upper and lower level in order before pouring to oppose weight and after pouring to oppose buoyancy. Now, how to calculate buoyancy forces? We know that for any object immersed in a fluid, okay. So let's say here you have the core is completely immersed in the molten metal. So what you will have is that the weight is tending to move the core downward, but you will have a buoyancy force acting from the fluid on the core, and the buoyancy force is calculated as follows. The buoyancy force is equal to rho of the metal, okay, times the volume of the core. This is called displaced volume. We call it in fluids displaced fluid volume, okay. Now, since here the core is completely immersed into the cavity, then the displaced volume, so V displaced, is equal to volume of the core, okay. So we will say here that V displaced is equal to V of core, because since the core is completely immersed in the fluid. Okay, so of course when we talked about displaced volume, it is the displaced volume of the fluid, because when you put the core, it will take the place of the fluid, okay. So this is V displaced of fluid. And here, what is the fluid here? Here the fluid is the molten metal. Okay, now, so this is for the buoyancy force. Okay, this is how we calculate it. Now, concerning the weight, of course, for the weight, it's equal to, the weight will be equal to the density. So here is the difference. For the weight, we take the density of the core, okay, not of the metal. Density of the core times volume of the core, okay. While for the buoyancy force, we take rho of the fluid times the displaced volume of the fluid. But since here, as we said, the core is completely immersed into the fluid, then the displaced volume is equal to the volume of the core. So the buoyancy force will be equal to rho metal times V core. Okay. So now, if you want, in total, we will have a total lift force equal to the difference. Okay. So if you want, F lift will be equal, the lifting force will be equal to the buoyancy force minus the weight. And if we replace the buoyancy force by its expression, which is rho metal times V core, minus the weight, which is rho core times volume of the core, you can see that the volume core is common between the two. So we'll take it into factor. So we get that it's equal to the volume of the core times rho metal minus rho core. And in general, the density of the metal is higher than the density of the core. In general, the core is made of sand, and you have, for the metal, you have, depending on the type of casting you are doing. See, here it's in an aluminum copper alloy. Its density is given. It's higher than the sand density. So if we want to replace numerically, we need first to get the volume of the core. Okay, to get the volume of the core, if you look well here, they gave us the weight of the core. The weight of the core is 15 kilograms. Okay, so this will correspond to W is equal to rho of the core times its volume. Okay, so since we have the density, here rho of the yes, exactly. It's the weight of the core. So rho of the core times volume of the core. Since rho of the core is given, it's 1.6 gram per centimeter cube. And the weight is in kilogram. Pay attention for units here, okay? Always check your units. So weight is given. You should pay attention for something. When they give you the weight in kilogram, what should you do? You should multiply by G, because you know that weight is M times G. Okay, so sometimes instead of giving directly the weight in Newton, they gave us the mass, and the mass, once we have it, we multiply by G to get the weight. So the weight is 150 Newton, and since we have, when you have a Newton unit, then you have rho in kilogram per meter cube. Okay, and the volume is, sorry guys, just 1 minute here. W is mg, okay, but the weight is, if you want to calculate the weight function of the volume, it's rho v times g. And g will be simplified if you want, okay, because the weight is mass times g, and the mass is rho v. So you get that W is rho vg. So if you want, you can simplify g directly, okay? Or you can put it in the equation, and then it will be simplified again, because you will replace g by that. So from beginning, if you want, we can simplify g from here and from here. So we get just that the mass is rho times volume. And it's, if we remove the weight, so we have M equal to 15 kilogram equals to rho of the core times volume of the core. Now, the volume will be in this equation in meter cube, okay? So if you replace, if you say that the volume here, you get V equals to M over rho, okay? It will be equal to 15 over, here you should pay attention, okay? Rho is given in, the unit of rho is gram per centimeter cube. So you need to convert it, okay? you need to convert it to a kilogram per meter cube. Or if you want to keep rho, in gram per centimeter cube, then you should convert your mass to gram, and the volume you will get will be in centimeter cube. Okay, so you can play with units as you like, just to have, you should have units that are convenient with, suitable with each other. So if you choose to keep rho in gram per centimeter cube, you can say here, I don't want rho in kilogram per meter cube. I want it in gram per centimeter cube. But in this case, my mass should be expressed in gram. This is why I should convert from kilogram to gram. So it's 15,000 gram. And then the volume I will get will be in centimeter cube. So I can deduce here that if I keep rho in gram per centimeter cube and I convert the mass to gram, then my volume will be in centimeter cube. So V in centimeter cube will be equal to M in gram over rho in gram per centimeter cube. So I will get 15,000 over the density of the core. The density, since the core is made of sand, so I should divide by 1.6. Then I can get the value of my volume in centimeter cube. And once I find V, all I have to do is to replace into the formula. So here I can replace V by 5,000 over 1.6, and then multiply by rho of the metal, which is 2.81. Also here, make sure that two densities have same unit. So which is here the case. It's in gram per centimeter cube. If not, pay attention to convert your units. So times 2.81 minus 1.6. And then you will get your lift force. Okay. What will be the value of your lift force? في شيء ناقص عندي بالايكويشن، مين بيقول لي شو هو الناقص؟ What is missing? No one told me that something is missing. What is missing? Exactly. G is missing. Okay? So here, when I find the weight, this is rho times V is the mass. So I should add what to the mass? I should add G here. And also the same for buoyancy. For buoyancy, okay, I should multiply also by G. Okay, so don't forget G here. So just you should add to this G. Okay. So here everything is, I can take G into factor also. So I will put here G and here G. So my total result will be here also I should pay attention for units. Okay. If I want my force in Newton, what should I do? Who will tell me? If I want to have my total force in Newton, what conversion should I do? What is the unit of G? G is like, the unit of G is like acceleration. Okay, it's meter per second square. Okay, now in general, you know that the force in general is in Newton. Okay, Newton represents what? It's M times A, mass times acceleration. So Newton is kilogram times acceleration, which is meter per second square. Okay, so if you want your value in Newton, you should make sure that when you do rho times V, okay, to have the units of kilogram and meter. not gram and centimeter. So what you can do is after calculating this term, V times rho, when you do V times rho, okay, you will get your value in gram here, okay? Because you used V in gram per centimeter, you used V in centimeter cube, and you used rho in gram per centimeter cube. So when you multiply, you will get your value here in gram. So if you want to convert to Newton, what you get here is gram meter per second square. So to convert to Newton, what should we do? We should divide by the result by 1000. Okay? So, or you put just your unit as gram meter per second square. But if they ask for Newton, you should divide the result by 10, by 1000. So when you divide the result by 1000, then you get kilogram meter per second square, which is the unit Newton. So just all the issue here mainly is to pay attention about units, because everything else is very, very simple. Okay? So let us check together the calculation. So first, the first step, okay, I can calculate the value of here, for example, they converted the density to kilogram per centimeter cube from beginning. You can do this also from beginning, work with kilogram per centimeter cube. So once you do this for the core volume, you can find it, okay? And once you find the core volume, you applying the formula for you can find the displaced weight, okay, as we did together. It's the displaced weight is rho Vg, okay, and where V is the volume of the core because it's completely immersed. Rho is the density of the metal, and G is the gravitational acceleration. So we can find the weight of the displaced volume. And once we find the weight, here, because they converted the densities to kilogram per centimeter cube, they directly found the value of, if you want, the value of the mass directly in kilogram. Here, for example, they are putting displaced weight, but they are keeping kilogram units. And they mean this is the mass, the equivalent mass, okay? So the whole thing to do at the end to have it, to convert it to Newton, is to not forget to multiply by G, okay? So when I multiply by G, I go from unit of kilogram to unit of Newton. So buoyancy force will be the difference between the weight of the displaced volume, which is the upper, if you want the upper force, okay, minus the weight of the body. So this is the total lift, if you want, okay. In general, we consider that the buoyancy force is the one that is acting upward, and the weight is the one downward, but the resultant here lift force, okay. So which is the force that will act overall on the core, which is the difference between the upward force and the downward force. So you can get the value of your total lift force. Okay? Any question on this? Okay. So we will continue if you want. For now, this is the problems of chapter 7-8, but I posted for you an assignment on to practice more. And after we will correct the, now we will continue with chapters. And after, to do revision for the exam, I will correct the homeworks with you. Okay? So now try to do the homework on chapter 7 and 8. You can start to do it. And make sure to complete chapter 8, part 1, part 2 until Friday. Okay, so Wednesday you can have, if you didn't finish the videos, because the videos are a little bit long for chapter 8. So make sure to finalize them. And on Friday, you hopefully will start a new chapter. Okay? Yeah, let's see. If you don't have any questions, see you next time. Bye bye.